Okay, so we are going to move on to some geometry. So everything we've kind of gone over before this will definitely help in solving for some of this some of these skills. So the first lesson we're going to do is similar figures, and it starts on page 4. And it says similar figures have the same shape, but not necessarily the same size. Similar figures have the following properties. So you probably learned the difference between congruent and similar figures in the past. Congruent means they're like the exact same. They're the exact same shape, exact same size, have the exact same size angles and sides, whereas similar figures are the same shape, but they're almost either enlarged or made smaller. So, for example, these two shapes are similar. They're flipped, but they are both triangles, obtuse triangles. And we'll figure out by doing some work down here that one is to scale of the other. So they have the same angles actually, but the size of their sides are actually different. So in this case, their corresponding angles are congruent, which means they're the exact same degrees. Their angles are the same, but their corresponding sides have proportional lengths, which means this side, this side down here and this side down here, the way that they relate to each other will be the same way that this side and this side relate to each other. So what is the measure of angle D? So if you take a look at these, I just said that they were flipped. So angle A and angle D are going to be corresponding angles. So angle D corresponds to angle A. Since angle A's measurement is 21 degrees, so does angle D's. So angle D measures 21 degrees. So that's one way you can tell that they are similar figures, is if one of their corresponding angles, especially in a triangle, is congruent or the same size. Example 2, what is the length of DE? So this is the missing length that we're trying to find right here, is DE. The lengths of corresponding BC, this side, and EF are given. So this is the corresponding side to this. So if I flip this over and made them kind of look the same, these two would be the same side of the triangle. So those are corresponding, not congruent, but corresponding sides. So the length of AB is given. This is the one that we know, but this is the one we don't know. You need to find the length of the corresponding side, DE or ED. So you set up to solve the proportion AB, this is AB over DE. So we have AB over DE. So this is the one we know, and this is its corresponding that we don't know. BC we do know, that's 5, and EF we do know. We're going to put those underneath each other like this. So we have 4 over the unknown number equals 5 over 2.5. So if you take a look, what are we doing? We're going to do cross multiplication here. So we're going to multiply this one with this one and this one with this one. So 4 times 4.5 is 10. 4 times 4.5 is 10. And then 5 times x is 5x. And then you solve for x by dividing this by 5 and dividing this by 5. So 10 divided by 5 equals 2, and 2 equals x. So the length of DE is 2 meters. So in order to find your proportion here, or your missing length of your proportions, you cross multiplied. So you multiplied this numerator by this denominator and this numerator by this denominator and kept them equal on each side to find the missing proportion of this. So our draw is to draw a pair of squares with different side lengths. Are the squares similar? So here's a square, and squares all have the same size sides, right? So if this is 4 centimeters, and this is 6 centimeters. Are they similar? All squares are going to be similar, right? Because they all have 90-degree angles, no matter what. That's like a characteristic of a square, right? And they all have 4 equal sides. So they're all going to be similar. They may not be congruent. This definitely is not congruent because it's not the same size side, but they are similar because they all are going to have the same length sides and the same angles. They all have corresponding angles and congruent angles. All right, let's keep going. Is triangle KLM similar to triangle XYZ? So let's just take a look at this really quick. So we have this triangle and they're set up the same, which I like because you can kind of see the corresponding angles and then the corresponding sides. So obviously this K is the corresponding angle to X. So angle K is equivalent to angle X because they're both 90 degrees. Yes? All right, so let's see what we have to do here. Angle K corresponds to angle X. The symbol shows how each is a right angle, so it measures 90 degrees. Angle L corresponds to angle Y, and angle M corresponds to angle Z. Okay, so this one matches this one matches this one. The angle marks show that both of these pairs of angles have equal measures, so all pairs of corresponding equals are congruent. And what that means is, like, if you look at this angle, it has 2 arcs there, or 2 lines, to show that it's different from the one that has 1. Well, because these are lined up next to each other, and we're questioning whether they're similar, the fact that this has 2 and this has 2, you know that they are the same size angle. And if angle K is equivalent to angle X and angle M is equivalent to angle Z, you wouldn't even need to have that marked there. You would know automatically that L and Y were congruent and they're corresponding angles, but they're also congruent. How do you know that? Because when you add up the angles of a triangle, the sum of all the angles of a triangle equal 180. So if these 2 equal the same and these 2 equal the same, then you know these 2 have to equal the same too, because they both triangles have to equal 180. All right, let's keep going. Do the corresponding sides have proportional lengths? So we're going to look at this side compared to this side compared to this side, and this side compared to this side. Let's see what they have for us down here. KL is 5, XY is 10, 5, 10. We're gonna simplify that to make it 1/2. So that's what we're trying to find here. They all should be 1/2 of each other. So LM, and this is LM, and YZ, 13 over 16 is also equivalent to 1/2, and KM and XZ, so KM is 12 over 24, which also equals 1/2. So all pairs of corresponding sides have lengths in the ratio of 1 to 2, or 1/2. Triangle KLM and triangle XYZ are similar. Yes, they are. They are not congruent triangles because they are not exactly the same, but they are similar because they have proportional sides and congruent angles. What must be true of corresponding angles in 2 similar figures? They must be congruent or equal. So in 2 similar figures, the angles have to be the same degrees. The sides don't have to be the same length, but the angles need to be the same degrees. So the corresponding angles must be congruent. If 2 figures have the same shape and the same size, Are they similar? Explain. They are, but they are also considered congruent. So it's kind of like all rectangles are quadrilaterals, but not all quadrilaterals are rectangles. All shapes that have the same, all figures that have the same shape are similar, but they're not necessarily all congruent. So if they're the same shape and the same size, they're similar, but they're also congruent. So yes, but also congruent. Identify each pair of figures as similar or not similar. Explain why or why not. All right, so the first thing we need to do is look at the angles. Are the angles are the corresponding angles congruent? Well, these are rectangles. These first two are rectangles, and the way I know that is because first and foremost, it has 4 sides. It has 2 pairs of parallel sides. It has 2 pairs of equal sides, and it has 4 right angles. So both are rectangles, which means all the corresponding angles are 90 degrees, which means they're congruent. So I'm just going to write down here, congruent corresponding angles. So that's one reason why they could be similar. But now we have to check the corresponding sides to see if they're proportional. So we're basically going to compare them and make sure they're all the same proportion. So if I look at this one and this one, that's 2/3, right? So we've got xz over tv. Actually, I'm going to flip them around and do tv, the smaller one on top, and xz equals 2/3. And then these two right here, 5/6. So st over xy equals 5/6. So are these the same proportion? Like, can I do something with 2/3 to get 5/6? I can't, right? So like if you were to cross multiply those, it wouldn't work. I can't do anything, like they're not the same proportion. So 2/3 does not equal 5/6. I can't do anything to 2/3 to get 5/6. I can't do anything 5/6 to get 2/3. So that means they are not similar because the sides are not proportional. All right, let's take a look at this one. So take a look at the angles. So this angle is corresponding to this angle. Angle J is corresponding to angle M. Angle K is corresponding to angle N. And angle L is corresponding to angle P. So this is a isosceles triangle, right? Or no, it's an equilateral triangle, but it has 2 equal angles, right? So M and P and J and L are all equal. So it looks like all of the angles, all the corresponding angles are they're congruent. So I have all congruent corresponding angles. Yes, that works. Now let's take a look at, so this is no. Let's see if the corresponding sides are proportional. So let's compare this one to this one, and then we'll compare this one to this one. Since it's a isosceles triangle, we only need to do 2 of the sides to see, because then if we know that this side and this side is proportional, this side and this side will also be proportional. So I guess it's not an I said equilateral triangle earlier. It is not. It is an isosceles, 2 equal sides. All right, so if we do 5/15, I'm doing this side with this side, and then I'm doing 6/18. 6 over 18. So are these equivalent fractions? No, they're not necessarily, but if I were to reduce both of them, here, I'll rewrite them. I'm gonna not write equivalent fractions, but if I were to reduce both of them to its simplest form, would they be equivalent? So if I divide both of these by their greatest common factor, which is 5, I get 1/3. And then if I reduce this to its most reduced form, which is dividing the numerator and the denominator by 6, I get 1/3. Right? So in all intents and purposes, these are equivalent fractions because they both reduce down to 1/3. Another way of thinking it is if you could have reversed those, 15 over 5 is equivalent to 18 over 6 because 15 over 5 is 3 and 18 over 6 is 3. So is this similar? Yes, it is because corresponding sides are proportional. All right, these what are these, rhombuses down here? Yeah, they're rhombuses. How do I know that? Because they have 4 sides, 2 pairs of parallel sides, and 4 equal sides. So if you look at the angles right away, so this is the corresponding angle to this, and this is the corresponding angle to this. Are they the same? No, they're not. So right away, you know this is not similar because the corresponding angles are not congruent. You don't even need to worry about the sides are not congruent. You don't even need to worry about if you look at the actual sides, the sides are actually proportional. So they're 1/2 of each other, right? And because they're all the same, you know they're going to be 1/2 of each other no matter where. So like 5 is 1/2 of 10, 5 is 1/2 of 10, and so on. However, because you first check the angles, that's like the first thing you do. And if the corresponding angles are not congruent, then it automatically takes it out of the running to be similar. All right, so you are going to do the rest of these. You're going to find out, so what are you doing here? For each of the following, find the indicated measure. So what you're trying to do is figure out the missing measure of either a side. So you're trying to figure out this side on this one. You're trying to find out this angle here. And this big triangle is corresponding to this smaller or is similar. It says right here that this triangle is similar to this triangle. So what's this corresponding angle to T? Down here, these two triangles are similar. It says right here that they definitely are similar. And so you're trying to find out what is the corresponding angle to J. So a hint there, this triangle is flipped over. And then this triangle is similar to this triangle. The big triangle and the small triangle are similar. So if you know that this is 10, what is this longer one? So I think with this one, you're gonna have to do some cross multiplication here to find that missing length. So you know that 18 and 12 are proportional. So if you do 18 over 12, and so then the larger triangle is the one, or the length of the larger triangle is what we're trying to find. So that's the unknown number. And so we do know that the smaller one over here, the corresponding one, is 10. So if you cross multiplied that, you should be able to find out what 10 is, or what x is. So you would do 12 times x equals 180, and then solve for x, and that should give you L. You could do that, or you could just try and find out what the missing is by reducing this. So like 12/8, ooh, sorry, you can't see that. 12/8 in its most reduced form, 6, so divided by 6 equals 2/3, yes? So then if you wanted to make 10 over x equivalent to 2/3, what would you do to these? Like, how would you figure this out? What would this be if it was equivalent? Or then again, you can also cross multiply this to make it simpler. So 30 equals 2x, x equals. All right, so you can finish that one. And then these are the ones that I love, love, love. It's like the real world problems using algebra and geometry. Clara is 5 feet tall and casts a shadow 8 feet long. At the same time, a building casts a shadow 32 feet long. What is the height of the building? Whew. All right, so you're basically finding, so this is a triangle, and then you've got your larger triangle, right? So this is her shadow, and then this is the shadow of the building. So if you know what her height is, 5 feet, you should be able to find out what this height is using the proportions of 8 to 32. So 8 over 32 equals 5 over h. So if you cross multiply, you can solve for h, or if you simplify this fraction right here and find the equivalent fraction to whatever this could be, you can solve it that way. I think it, man, I'm sorry, you can't see that. I think it's easier just to cross multiply or simplify than cross multiply. So 8 over 32 is 1/4 equals 5/8. Now cross multiply, so 1h equals 20, which equals, so this would, h would equal 20. So the height of the building is 20 feet. So I just gave you that one. So you can try and figure out this other one. It's about a distance across a lake. Whether it can't be directly measured, so you have to draw this diagram to figure out the length across the lake. So you have to figure out, looks like, what D is. So D is a corresponding length to this 21 meters over here. So because you know this and you know this, you should be able to find out what D is using cross multiplication or simplification of, oh, did I skip a page? Of fractions. I think I'm missing a page here. Nope, we did it all. All right, next lesson is scale drawing. So this is taking what you just learned in that lesson and like being able to actually draw the a scale or come up with another measurement for something either larger or smaller. Scale drawing makes it possible to represent objects accurately that are either too large or too small to draw at their actual size. The scale is the ratio of dimensions of drawing to the dimensions of the actual object. I think we did this when you were in 5th grade in MTSS. A scale drawing and an object it represents are similar figures. Just as you can set up and solve proportions to find missing lengths in similar figures, you can set up and solve proportions to find actual lengths and areas from scale drawing. You can also use proportions to create your own scale drawing. So a biologist made this drawing of a spider he observed. What is the actual length of the spider? Write the ratio to represent the scale. So the scale is 5/10 of a centimeter equals 2 millimeters. So the ratio is 5/10 of a centimeter over 2 millimeters. So he drew this larger spider right here, but the actual spider's larger or smaller? It's smaller. Because each one of these centimeters is actually worth 2 millimeters. So write the ratio that includes S, the actual length of the spider. So S is going to be our unknown number. So the scale drawing length, so this is the drawing, this is what he actually drew, is 2.5 centimeters over the actual length, which is S millimeters. We don't know how much the actual length is. Set the ratios equal and solve for S. So 1.5 centimeters is equivalent, and I need to put centimeters because we're going to have to change this, is equivalent to 2 millimeters. So that's his scale that he gave us. Each one of these centimeters is actually equivalent to 2 millimeters. And what do we know? We know 2.5 centimeters. We keep those lengths together, and we don't know the actual spider. So we cross multiply. So 0.5 times S is equivalent to 2.5 centimeters. Can we do that? I guess we can. 2 millimeters times 2.5. I thought we would have to change it into centimeters, but I guess we don't. So then you solve for this. This equals 10, or this equals 5. 2.5 times 2. So 0.5 S equals 5. So what is 0.5 divided by 5? So 0.5 divided by 5. So you can do that with a calculator, or you can actually solve it. So 0.5 divided by 5. Or no, sorry. 5 divided by 0.5. 5 divided by 0.5. So you obviously, I know you learned how to do this last year. You cannot divide a whole number by a decimal, like to actually do it out. Now, I know you probably can think in your head how many 1/2s can fit into 5, 10 can, or how many times can you break 5 up into 1/2. But to actually do it mathematically, in order to move this decimal over, you got to multiply this by 10, and then you have to multiply this by 10, so it becomes 50. Now 5 can go into 50 10 times. So that's pretty interesting. So the scale, the actual spider is 10 millimeters in height. So he drew it out as 2 centimeters, but if he would have only done 10 millimeters, it actually wouldn't have been that much smaller, because 10 millimeters is equivalent to 2 centimeters. So the actual spider would probably be like this high. Not this high, because this is about 10 millimeters. Oh, wait, no, I'm wrong. It would be about this high, because 10 millimeters is equivalent to 1 centimeter. So the actual spider would only be about that big, whereas he enlarged it so you can actually see it. All right, this explain. Is a road map an example of a scale drawing? Explain why or why not. Yes, it is. Why? Because the roads are like scaled down, right? So you can actually fit them on a piece of paper. If a road map was as big as the actual road, you wouldn't necessarily be able to use it, right? So a road map is a smaller scale of the actual thing. So you can use it, right? It's made smaller. Okay, but the mileage is all the same. So like on a road map, I know like you'll have that like map scale down here sometimes on a road map. And it might say like this, like 1 inch equals 10 miles. So for every inch that's on the map, that's actually equivalent to 10 miles when you're driving or walking or biking or on your scooter. At the right is a scale drawing of a school music room. What is the actual area of the music room? All right, so you write the ratio to represent the scale. So I have 1/4 inch over 3 feet. This is the ratio for every 1/4 inch that's actually worth 3 feet. Measure the length of the length and width of the drawing. The length is, let me pause this, and I'm gonna go grab a measuring tool.